All right, so 2.2, polynomial functions of higher degree. So we're going to be talking about x cubed, x fourth, x to the fifth polynomials. So last section was all about quadratics, so those were x squared. I just want to remind you, polynomials, they have graphs that are continuous, meaning they have no gaps or breaks or holes or asymptotes, any of those things going on. We can just follow them smoothly. If we trace it, there shouldn't be any point where we are not following along the graph. They have smooth, rounded graphs. They shouldn't have any sharp points like absolute values or other types of functions we might run into. Now, that might not be obvious when we graph them initially, but as we adjust the viewing window, we should be able to see that. So here are a couple examples. So we have on the left, this is actually a cubic and x cubed polynomial. Notice how it's got a nice smooth curve. And then here is actually a fourth degree polynomial, x to the fourth. And again, a nice smooth curve. I do want you to look and see how the y-axis, the scaling in particular along the y-axis, has been adjusted. We'll go over specifically how to do that, but that's going to be something that's important to get a nice view of our polynomials to adjust the y-axis. All right, so you do that by clicking this wrench icon in the upper right corner, and I'm going to start here. So from negative 100 on the bottom of our graph all the way up to positive 100 on the top, and then counting by 10. You could make adjustments from there, or you could zoom in and out from there to make sure your graph fits well. That's going to be a place that I'm going to start off with, unless I know something else about the function that leads me to believe I need different settings. So let's go ahead and do that. So I'm going to graph these two functions, and I'm going to kind of adjust the scaling until it seems appropriate. So I went ahead and typed this one in. That's our first one. And you can see it just kind of looks like it's shooting up and down, and we can't really see anything. So click right up here in the graph settings. And I'm going to adjust this to be negative 100 on the bottom. I just click in there and then type that what I want. So all the way up to 100 on the top. And let's go ahead and count by 10. You can kind of turn on or off these minor grid lines depending on your preference. Doesn't really matter. All right, so that shows nicely. For a polynomial graph, you're going to want to make sure you see your x-intercepts clearly. That's important. You may want to be able to see your minimum values and maximum values. And then sometimes the y-intercept is of interest. So any of these points of interest, you want to make sure that you could easily see them on your graph. Okay, so this was in standard form, right? It's descending order of powers. We could also have a polynomial that's in factored form, like that second one that I had, g of x. Now, I already have my scaling set, so maybe this will work. Oh, okay, all right. So this sort of works. I can drag the graph to maybe see where it needs to go. That's not quite perfect there. I actually want to make an adjustment. It looks like I need to go up at least to a little bit over 150. So I can make my adjustment to my maximum value and say I need to go up to, let's go 180. Okay, cool. Now that lets me see everything I'm looking to see. So I can see my x-intercept values here. I can see a couple maximums, a absolute maximum up here, a relative maximum, a relative minimum. I can see even the y-intercept, which is actually really close to that relative minimum. You want to be able to see all of these things, and it kind of just depends on what you're using the graph to do. All right, so remember, graph settings, and you can adjust it. You could even adjust your x-axis if you want to. I mean, technically my graph, most of the important stuff happens between -4 and 3, so I could do like from -5 all the way over to 4 if I wanted to sort of zoom in that way as well. I don't really need to do that, so I'm not necessarily going to. I'm going to go ahead and go back to the notes here. All right. Okay, So the end behavior of polynomials. So what's happening on the ends? Are both ends going up? Are both ends going down? Is one going down and one going up? One going down and one going up? Those are all of the different options. Sorry, up and down. Different options for the end behavior. And so we're going to look at what factors, not factors like we would think of for polynomials, but what things about the equation can tell us what type of end behavior we're going to have. So I have this nice handy chart. There's two things that the end behavior of our polynomial is going to be based on. It's going to be based on the degree of the polynomial, so the highest exponent power. That's whether it's going to be even or odd. And then the leading coefficient, whether the leading coefficient, the number in front of that, is going to be a positive number or a negative number. Now, end behavior is based on sort of the highest exponent power is going to take over. It's going to dominate the equation, right? The bigger the x value gets, or the smaller it gets, the larger negative value that it gets, the more that highest exponent is going to sort of dominate the behavior. So the graph is going to either go up forever continually as we go out to the right, or down continually as we get a bigger and bigger x value. And we can just sort of see what's happening. So if we have an odd degree and our leading coefficient is positive, this is what's happening. As the x value increases, as we move out to the right on the graph, the polynomial is going to go up. It's going to grow up to infinity. And then as on the left side, it's going to go down to infinity. So as the x value gets smaller and smaller, or a bigger and bigger negative value, then it's going to go down forever. Even degree, so if we have an even degree and the a value is positive, so like a quadratic, this sort of looks like a quadratic, it's going to be going up on both ends, up on the right, up on the left. That's because with an even degree, when we square a positive number or square a negative number or raise to some other even power, we're going to get positive values from going up. And as we keep moving on, these are the different behaviors that we can have. Now, the way that we determine the end behavior is called the leading term test or the leading coefficient test. We check to see if the degree is even or odd, and we check to see if the leading coefficient is positive or negative. Here's a kind of a quick chart that we can look at. You know, the degree on top, is it odd or even, positive or negative? I just kind of condensed all that information from that previous chart into this one a little bit easier for just talking about the end behavior. All right, so let's look at these here. So on our first one, we have a leading term is right here. We have an odd degree. So 5 is an odd degree. And the leading coefficient in this case is a 1. So that's actually a positive leading coefficient. So if we kind of look back at our chart, or just kind of what we know, odd degrees go different directions, up, down, up, whatever. And positive means that we're going to actually be going down on the left side of the graph and up on the right side of the graph. So as x approaches negative infinity, that's on the left side of our graph, then f of x is also going to approach negative infinity. It's going to go down forever. And on this side, as f of x approaches, as x approaches positive infinity, so going to the right, our graph is also going up. It's going up to positive infinity as well. Or easier way to say, down on the left, up on the right. So this one is a little bit easier. It's in standard form. It's already right there. Our leading term is just right there in front of our face. Pretty easy to figure this out. It's not so easy if things are not quite there. So that is not what I meant to do. Let's just go ahead and delete that. All right. It's not so easy if it's in a factored form, though it's not too hard. So we really just need to know the leading term, right? So we need to know x to what power and what's the leading coefficient. So we can kind of look and see, without multiplying everything out, we can sort of see what that's going to be. Because we have an x, and an x. But be careful, this one is actually eventually going to be squared in there. So as far as our x's go, we have x squared times an x times an x. So in total, that's going to be x to the fourth. We're going to get an x to the fourth power as we're multiplying this all out. And this number out in front, well, that's the only coefficient we're going to get for that x to the fourth, because none of these other x's have any number in front of them. They're just 1. So our leading term, we can sort of figure that out without actually multiplying everything out, which would be pretty tedious. So we can see we have an even degree and we have a negative leading coefficient. So that is going to be actually going down on the left side and down on the right side. Or more formally, as x goes to negative infinity, so to the left on our graph, then our function is also going to go down. It's going to go down to negative infinity. And as x goes to the right, so as x goes to positive infinity, then our function is going to go down to negative infinity. It's going to go down forever. This is the formal way to write it. I'm also okay for us right now. Just say that it's down on the left, down on the right. Another way we could do this is we could graph this on Desmos and kind of check out the end behavior that way too. Same here, if we don't feel confident with this leading coefficient test. But the point here is to understand this leading coefficient test and what it's telling us. All right, let me clear this and move on. Okay, so right now we were just talking about what happens on the end, what happens at the extremes as we go to positive infinity on the right or negative infinity on the left. What's the graph doing? But what about what happens in between? So first thing, I have a little bit of a typo here that I forgot to edit, but that's okay. We'll edit it right now. It's going to have up to n minus 1 terms. So a polynomial of degree n will have up to n minus 1 turns, or we also can call those turning places a relative minimum or relative maximum. They might not be relative, right? If we're talking about a parabola, could be an absolute minimum or an absolute maximum, or even some other graph could be absolute. Up to n minus 1 turns. So again, using that example of a quadratic creates a parabola. A parabola is x squared, right? Degree of 2. It has 1 turn, 1 relative minimum or 1 minimum value. And up to n x-intercepts. So if the degree is n, there could be n x-intercepts. So a degree of 2 could have 2 intercepts if this is our x-axis. Or it could have 1 if our x-axis is right there, just passing at the vertex. Or it could have 0, right? Doesn't cross the axis at any point. So that's why we say up to. It's not guaranteed to have that many. That's the most that it could have. You can see that no matter where we draw the x-axis here, there's no way for us to have more than 2. All right. A degree 3 graph. So let's just look at x cubed. So a degree 3 graph, not x cubed, not just that simple function, but it could have 2 turns, right? Degree 3 could have 1, 2 turns. Depending on where the x-axis is, right? It could cross 3 times, right? 1, 2, 3 if this was our x-axis. Or it could cross once or even twice if it was something like right here where it just touched there and then crossed over here. So this is kind of all the arrangements. What you should notice here is that there is no way for a third degree to have 0 x-intercepts. There's always going to be at least 1 because of the way the graph is going up forever, down forever. There's nowhere that x-axis could fall where it would have would have 0, less than 1 x-intercept. That's kind of an interesting. That's actually true for all odd polynomials, odd degree polynomials, because since it goes up and down, either way, down and up or up and down, it's no matter where the x-axis falls, it's going to hit at least in one spot. And then every polynomial graph will cross the y-axis in one place. Now, you can see that because anywhere the y-axis were to fall, it would only intercept the graph in one place because these are functions, right? That's sort of like the vertical line test in a sense. There won't be any more than 1 intercept, and there also won't be any less. All right. Clear this real quick. again, up to n minus 1 turns. So a degree like a degree 7 polynomial could have 6 terms, but it could also have 6 turns, but could also be less, right? It could be 1, 2, 3, 4, 6, right? It could do something like this where these are 6 turns, or it could just have less. It could have almost none. It could be something like this, depending on obviously the equation at hand. So up to is an important concept there. All right. Let's go ahead and take a look at this particular example right here and answer a few questions about it. So a polynomial right here is graphed here. Nice scaling already. What is the degree of this polynomial? Well, since we have the equation right there, it's easy to see that the degree is 3. So this is a third degree polynomial, but we could also look at it and see other things about it. We know it crosses the x-axis 3 times, so we know that it's at least a third degree. It could be even higher than that too. There are 2 terms, so add 1 to that's at least a third degree polynomial as well. But since we have the equation right on hand, we already know the answer. What is the end behavior? Well, that's easy to look at. It's down on the left side, up on the right side. So as x approaches negative infinity to the left, then the function approaches negative infinity, goes down forever. And as x approaches positive infinity to the right, it's also going up to positive infinity. Or we could just say that it's down on the left, up on the right. How many turns does it have? We just sort of counted those turns. Another way to think about turns is any minimum or maximum values, either overall minimums and maximums or relative ones like these. So there's 2. And how many x-intercepts? So 1, 2, 3. And they are at -3, 2, and 4. Those are our 3 x-intercepts there. Okay. Okay, here's an interesting question to think about. What would you guess is the degree of this polynomial and why? So I want you to take the information you know about the end behavior, the intercepts, the turns, all that stuff to make a reasonable guess about what the degree is. And go ahead and pause it and try to make that guess. Okay, I'm going to go ahead and answer. I think this is a 4th degree. Couple reasons. I know it's going down on both sides, which means that I'm dealing with an even degree. I can see that there are 3, maybe 4, it's hard to tell, x-intercepts, 3 or 4 x-intercepts. So if it's 3 x-intercepts, it could be 4th degree, right? Couldn't be 3rd degree because 3rd degree is not an even degree. So it could be 4 or higher. If there's 4 x-intercepts, and I know the minimum it could be is 4, so that's kind of giving me a little bit of a hint. There are also, looks like 3 turns or 3 minimum maximum values here. So my guess is 4. Now, that's not the only answer. Without more information, it's possible this is a higher degree polynomial, but I think 4 is a reasonable guess based on all this information, that it's even, that we can see that there's 3 or 4 x-intercepts depending on what's going on there, and the 3 turns. So all that stuff together is leading me to believe that this is a 4th degree polynomial. All right, now I'm gonna go ahead and pause right here. This will be the second part of the video, and I'll see you with that one.